Thank you, Laura. Thanks for the invitation. Thanks to Samory for driving me down here. Yeah, it's good to be here. And, this is informal, so feel free to ask questions at any time or to answer questions. So this talk is going to summarize three things I've done, or at least been trying to do over the last year, that fall under this heading of learning from multiple bias sources. And these are the three topics, which I'll just go through in order. And I do have some collaborators, which I haven't written down. So my collaborator on the first project is an undergraduate at Michigan, Jinshin Zhang. And on the second problem, it's a master's student at Michigan, Yuren Zhang, and Aniket Deshmukh, a former PhD student. And then on the third project, this is continuation of work with a former PhD student, and then ongoing work with a PhD student that Laura and I are co-advising, Alex Ritchie. Okay. So let's start with this first problem. And this, since I'm covering three things, it'll be at kind of a high level, but if you ever want me to go into more detail, let me know. So this is the problem of classification with corrupted data sets, and in particular, multiple corrupted data sets, where each data set possibly has a different degree of corruption. So one motivation is that you have several unlabeled data sets, and you have an unlabeled data set, and you have different annotators who provide labels. And each of those annotators is possibly noisy, so they each create their own labeled data set, and you can think of those as having multiple noisy data sets. And so this could be in a crowdsourcing setting where the annotator is a crowd worker, or in this framework of data programming where the annotator is just some simple heuristic program that you write. In our case, this work was motivated by the problem of learning from label proportions, which is a weak supervision problem that can be reduced to this more general problem, which I can say more about if you're curious, but otherwise I won't take the time to do that. All right, so I'm going to be talking about how to formalize this problem of learning from multiple corrupted data sets. And let's just begin by talking about the problem of classification with a single data set with label noise. All right, so here's a model for how that can be generated. And this is what you would call random label noise, as opposed to adversarial or some other type. And binary classification, so we have training data, and the tilde indicates that the labels are noisy. All right, so this can be generated according to this model, where in the first step you have uncorrupted data drawn according to some joint distribution P, but you don't get to observe the Y's. Those are unobserved. And then with some probability, those labels get flipped to the other label. And it can depend on the class. So the label gets flipped. So the observed corrupted label is the opposite of the true label with some probability, row 1 or row minus 1, depending on the true label. So what you might do if you sort of just ignore the label noise is empirical risk minimization. But unfortunately, because of the label noise, that's typically not going to be the right thing to do. That's going to bias your solution in some way. And so what has recently been, well, I say recently, probably the conference paper on this probably came out about 6 or so years ago. In a more recent journal paper, there's a method of Natarajan et al. For taking any loss function, any loss you might use for binary classification, and modifying it. And they call it the corruption-corrected loss. And it requires knowledge of these label noise proportions. So let's assume those are known, rho 1, rho minus 1. And so you take your original loss of interest and you define a new loss, L rho, just in terms of the old loss and these label noise proportions. And you also need to assume the sum of the two proportions is less than 1, which is a little bit like saying that the total amount, that most of the labels are correct. All right, it also makes this denominator positive. So what they show is that if you take the expected value of this corrected loss with respect to the corrupted data, it equals the uncorrupted risk with your original loss. All right, so the thing on the right is what you'd like to minimize. The thing on the left is what you can actually estimate because you have data from this corrupted data set. So this suggests learning a classifier by doing empirical risk minimization or using this corrected loss and the noisy data.
And this is any loss function?
I think that's right. Yeah. So there is an assumption which I glossed over. It's that you need your f of x to be such that, you need f to be such that this quantity is bounded. So you could do that with by taking a bounded loss, or you could take a bounded function class in some sense, like a ball in a reproducing kernel Hilbert space, which is what I'll be doing. Yeah. Okay. So we took this as our starting point. And our idea was to see if we could build on this in the setting of learning from multiple corrupted sources. So here's our setting. Again, there's a single clean distribution P, and we want to design a classifier that's optimal with respect to this distribution. But we don't get to observe clean data from that distribution, but we get multiple noisy data sets from different corrupted versions of that. So in particular, assume we have capital N total data sets, and for each data set there's a set of label noise proportions that are known. And let's let P rho I denote the ith corrupted data set according to this label flipping model that I described earlier. All right, so we have data according to those corrupted distributions. So what we decided to look at, and what seems like a natural strategy, is to look at some form of weighted combination of these corruption-corrected losses. So if you look at the term in brackets, that's just this corruption-corrected empirical risk for the ith data set, like I described on the previous slide. Each of these is already an unbiased estimate for the risk, but we're looking to take a weighted combination. So this is just W is just some probability vector, some convex combination. For any choice of the W's, this will be an unbiased estimate of the risk of interest by the result from the previous slide of Natarajan et al. But we'd like to see if we can set the weights according to some criterion to maybe minimize the variance in some sense. Right? So this is unbiased, but we'd like to minimize the variance. All right. So the main result is to do that by proving a generalization error bound and then choosing the weights to minimize that bound. Okay, so again, just a reminder, and to introduce notation, E of F is our risk. This is the uncorrupted risk of interest. L is the target loss of interest. And I'll take the set of classifiers to be just a ball of radius r in a reproducing kernel Hilbert space associated to some kernel. So the generalization error bound, and this is for any fixed set of weights, if you have a Lipschitz loss and a bounded kernel, K is the bound on the kernel, then with high probability, with respect to the draw of all of these noisy training data sets, you have this generalization error bound. So the left-hand side, recall, is just the expression from the previous slide that we proposed to minimize. And this is the thing we truly want to minimize. And those two things are close with high probability. And the closeness is captured by this quantity. All right, so what are we doing? In the case of a single data set, this reduces to the conventional generalization error bound for kernel methods. That's well known. But in this case of multiple noisy data sets, you see we have some terms here. Ni is the size of the ith data set. And then we have these label noise proportions. And then we have the weights. And out front, you've got the Lipschitz constant, the radius of the ball, and the bound on the kernel. Okay, so we proved this using some generalization of Rademacher complexity analysis, which I won't go into. But the key point is now we have a quantity that is, holds for any fixed set of weights. And furthermore, this bound is data independent, which means we can set the weights a priori to minimize this bound. All right, so this will be our notion of variance that we want to minimize. All right, so if you do that, it's just minimizing this bound is just a simple, you've got a quadratic objective, the weights here, and you've got a simplex constraint on them, so it's an easy problem to solve. And so this is what you have to solve to minimize this bound, and you can just work it out. It's very easy. The weights, the optimal weights are proportional to this expression. And this is something you could interpret as a signal-to-noise ratio. So it depends on the ith sample size, but also the label noise proportions. And the larger this SNR, the more weight you put on the ith sample. That's the basic idea. So does it make sense? Well, remember rho I1, rho I minus 1, these are the probabilities of flipping to the other class. And so when is this SNR large? It's large when those label flipping probabilities are small. And it's also large when they're close to each other. In other words, the noise is symmetric. Right? So both of those are, you can argue, are, it's reasonable. It makes sense that you would put more weight on the ith data set when the ith data set is less noisy, basically. So why is this interesting? Well, you can use a generalization error bound. One thing you can do with it is to prove consistency of an algorithm, namely that the risk of your weighted empirical risk minimizer converges to the Bayes risk. And if you do that with our optimized weights, you can get consistency in a much broader number of in a much broader class of asymptotic regimes compared to if you just take uniform weights, 1 over n for each data set. So if you just choose uniform weights, then to get consistency, you need all of the noisy, you need Ni, which is the size of the ith noisy data set, to go to infinity for each data set. You need all of the data sets to get bigger and bigger, whereas with these optimized weights, you just need one of the data sets to have size going to infinity. And intuitively, this is just because these optimal weights are putting more and more weight on that one data set whose size is going to infinity. So it has that, it recovers that desirable result. So then there's more to this story, which I'm not going to tell you about, so I can tell you about some other things, but
By uniform weights, do you mean
just,
like 1 over the number of data sets?
yeah, so WI equals 1 over capital N.
Okay,
That-
so where you ignore the size of the data sets.
Right,
You ignore the NIs.
right, right.
You would put more weight on a bigger data set, right?
Yeah.
If you're just doing something, then you
Yeah, I guess for me the naive thing would have been to just give weight proportional to the size of each data set.
Yeah, and then that would cancel this NI, and then you're just sort of pooling everything together.
Yeah.
But you're still using a different loss for depending on which data set it came from. Yep, yeah, that would, I think that would also have this property. What's down here, like it would also be in this first condition. What's also interesting is to think about asymptotic regimes for the noise proportions. Suppose those are going to 0 or something like that asymptotically. And that's another setting where these weights are better than what you proposed. Yeah. So in our paper, we also applied this to this problem of learning with label noise proportions, which is this weak supervision problem, and I won't go into detail, but it allowed us to prove basically the most general sorts of asymptotic results that are known for that problem. Okay. So any questions on this before I move on to the next topic?
Where did people work on learning that label noise?
Like learning the label noise proportions? Yeah, that's a good question. So in this application that we had, label proportions, the row I's are actually known. So that made it a good application of this theory. But if you had, but in general, you might not know these proportions, the row I plus or minus 1. And there are definitely techniques for estimating them. So like, for example, in crowdsourcing or data programming, they have their own techniques for estimating them. And then in this sort of IID setting here, I've worked on that problem, and others have also worked on how to estimate those proportions. So that's a separate aspect that you may need to combine with this in practice. Yeah. Yeah. Okay. So I'll move on to the second part. So sim-to-real reinforcement learning. All right, so here's just an overview of reinforcement learning. So there's an agent that in a discrete sequence of time steps interacts with an environment by choosing from a finite set of actions. Every time they take an action, the environment then they start in a given state, in some state, and the environment takes them to a new state based on the action, and also gives them a reward signal. And the goal is to maximize cumulative rewards over some time horizon. A common model is called a Markov decision process, which says that the next state and reward depend only on the current state and action and not on the history before that. So that's a very useful model for analyzing reinforcement learning algorithms. A theoretical framework for studying reinforcement learning is called PAC-RL, probably approximately correct reinforcement learning. And here's one setting for PAC-RL. So assume you have a finite state space, a finite action space. H will be the number of steps needed to complete a task. So a task here would be, maybe your agent is someone playing a game, and you play a game for a certain number of steps, and then it's over. A policy, denoted pi, is just a function that maps states to actions, so that's what governs the agent's behavior. V pi is the expected cumulative reward when following policy pi starting in the initial state. So let's just say you always start in the same initial state. All right, so V pi is a measure of, it's kind of like the analog of the risk from classification. It's just your performance measure for a policy. And then V star is kind of like the Bayes risk. It's the best possible value of V pi. So that's what you like to find a policy that achieves V star. All right, so an algorithm, and this is a little bit of a paraphrase of the formal definition. An algorithm is PAC if for all epsilon and delta, with probability at least 1 minus delta, the algorithm terminates and finds an epsilon optimal policy. So an epsilon optimal policy just means the V pi for the policy returned by the algorithm is within epsilon of V star. So you want that to happen with high probability. And you don't just want any PAC algorithm, but the goal is to find a PAC algorithm with a minimal sample complexity. In other words, you want it to terminate needing as few episodes as possible. Okay, so an episode is just the term for performing a task, right? So the idea is there's an agent. You start out, your algorithm is going to start out with some initial policy, and you'll perform the task repeatedly, updating the policy, and at some point you want to terminate and say, okay, I've got a pretty good policy. Okay, so that's how these algorithms, that's what you want. You want an algorithm that plays the game repeatedly and produces a PAC algorithm with as few episodes with a minimal number of episodes. Okay, so that's not sim to real. That's just background on reinforcement learning, but we're going to propose a framework for a similar framework in sim to real. So what is sim to real? Well, it's motivated by the fact that many reinforcement learning algorithms have a very high sample complexity. So you go to deploy them in a real environment, and they need a large number. They have to, large number of episodes to find a good policy, to the point where it's really not feasible in terms of, the cost of actually implementing a real system. So what people have tried is to first set up a simulator that imitates the real world, or perhaps multiple different simulators that are all capture different aspects of the real world, and to try to find a good policy by training on those simulators in hopes that it transfers to the real world and makes learning in the real world easier. Okay, so here's an example from a paper by Tobin et al. So these are some papers where people actually develop robotic systems that do this and show that this can work in practice. And so you might have simulators. There's some game or some task you're trying to perform. Here's the real world, and you set up some simulators that may not be exactly like the real world, but are close enough that you somehow learn the essence of taking action, the best way to take actions in this space. Okay, so we wanted to try to establish a theoretical framework for proving, to see if we could prove that you can actually get some gains in sample complexity in this sim to real setting. So far, all of the evidence that this works are empirical. And to do that, we're going to adopt a model called a rich observation MDP. If you're familiar with the POMDP, it's basically the same thing, but it's more or less the same thing, and I'll tell you what it is. But it's we're sort of using this terminology because of the work we're building on. So, in a ROMDP, at every time step, the agent observes a feature vector associated to the state, but not necessarily the state itself. So maybe the state is position and velocity, and the location of objects around you, but what you observe is an image from a camera, something like that. Okay, so that would be the observation vector, the feature vector. So a ROMDP, it's a generalization of an MDP, where you have this observation vector. And it's characterized by three things. So the distribution of the observation given state, the expected reward given the current state, observation, and action, and the transition dynamics. So the next state as a function of the current state and action. Okay, so these are in general, these will be unknown quantities, but they characterize the environment and how new states and rewards are generated by an agent. And we're just going to denote a ROMDP by a parameter theta. So it's not necessarily a finite parameter. It's just a notation for a ROMDP. So here's our theoretical model for sim to real, and it's analogous to the PAC RL setting from before. So we'll assume we have multiple simulators, so this tying into the theme of the talk, learning from multiple biased sources, and each simulator is going to be somehow not the real world, so it's biased. So there's B simulators, which are ROMDPs, these environments I just described, denoted theta 1 to theta B. And then there's a real-world ROMDP, theta R. And our assumption is that all of these parameters are governed by their IID draws from a common distribution on ROMDPs, denoted mu. Okay, so there's some unknown distribution on ROMDPs. All your simulators are drawn from that, as is the real world. A meta policy generalizes the notion of a policy. So it's a function that takes a ROMDP and a state and outputs an action. So you're going to the agent's actions are going to be dependent on the environment. That's all that says. So if you just fix the first argument to be any particular ROMDP, you just get a policy, as before. The performance measure is going to be, again, what you could call the expected cumulative reward of a policy, starting in the initial state and operating until it completes the task. But where now the expectation is with respect to not only the randomness of the environment, but also the random draw of the environment, theta. Okay, so this function pi of theta dot, that's just a regular policy. And so this v is the same v from before. And then v star will once again denote the maximum possible value of this. That's what we'd like. We'd like to find a meta policy that comes with an epsilon of v star. All right, so here's the learning scenario. And this is not the only learning scenario you could imagine for sim to real, but it's the one we studied. So the algorithm trains on the simulators. The algorithm has access to the simulators and can develop its policy by running episodes in the simulators. And then at some point it stops, and then it gets deployed in the real world. And it stops using the simulators, and it's deployed in the real world, and it gets to take actions in the real world and see which state it goes to, but it does not receive a reward signal. All right. Now, another setting you could imagine is where the agent does receive a reward signal in the real world. Of the previous work I mentioned, the empirical work, 3 of the 4 papers actually consider the one we're proposing right here, where they don't use real-world feedback to update their policy. They just use the observation of how the states evolve according to a given policy. All right, so our goal is to find an algorithm for sim to real that has a small real-world sample complexity, meaning it has, the real-world sample complexity is how many episodes your agent needs in the real world before it stops and says, I'm within epsilon of V star. And in particular, we would like that real-world sample complexity to be smaller than if we were training a single agent on a single ROM-DP with feedback. Yes?
But I thought you were caring about the real-world parameter theta r, and that the v that one should care about would be v pi of theta r.
Yeah, so that's a great question, and that's the distinction between these 2 settings that I described. So what Samory's saying is, don't view theta r as random. It's the real world. It's whatever it is, and it's not random. And you just want to do well in that particular environment. If you're going to do that, then you need to have feedback from the real world. What we're doing is we're saying this theta r is random, so the real world is also random. And so our performance is with respect to the random draw of the real world. Now you might, so when would this be useful? Well, maybe the real world is actually still simulated. So maybe there's a computer game. Maybe there's a computer game and you can play it in different configurations. And you want to practice without penalty in those sort of simulated models. And then you get a new configuration of the game, but that's also random, right? So, yeah, so the other model that you're describing, you would need to have feedback for the real world, because otherwise you're not going to be able to learn about a particular environment. Well,
I guess
without stronger assumptions.
Some additional assumptions that relate the theta 1 through theta b to theta r.
That's right. That's right. Yeah, you could make additional assumptions, maybe analogous to what they do in domain adaptation, transfer learning type of settings. Yeah. Yeah, so that's, I agree. There's a lot of different problems, formulations of this problem that would be interesting to look at. Yeah. Okay. So here's our main result. And let me just highlight the important part, or parts of it. So don't worry about the details of all the formulas. Epsilon and delta mean the same thing as before. H is the horizon, the number of steps in an episode. S is the size of the sample space. A is the size of the action space. F is the cardinality of this. So there's an assumption we make in our theory that the optimal meta-policy belongs to a known finite class of meta-policies, and its cardinality is capital F. Okay, so Under suitable identifiability and continuity assumptions, and I can say what those are if you're curious, there exists a pack algorithm for which at most this many episodes are collected from at most this many simulators, and at most this many no feedback episodes are collected from the real world. Okay? And our real concern is this number. We're okay if these numbers are larger because those are in the simulators. And we're willing to sacrifice sample complexity in the simulators to decrease sample complexity in the real world. So for comparison, the best known sample complexity for learning a ROM-DP, a single ROM-DP without access to simulators, but with feedback, is this expression. And so you can just compare. We do have a slightly smaller order here. And so that's our claim that we're actually realizing the benefits of sim to real. Okay?
What's the intuition why your bound does not depend on S?
Which bound?
I mean, the number of samples from the real world does not depend on polynomial on S.
Why is there no S in here? There's an S here, but not here. I don't have a good answer to that question. Yeah.
Sorry, what is
Capital S is the size of the state space, and he asked, why is there no S in here? Why is there no linear dependence on S? Why is it over here? I don't recall off the top of my head. Yeah, F is the cardinality of a prescribed function class of metapolicies. Yeah, so this part is very much an analogy with, this assumption about a finite class of metapolicies or policies is somewhat, well, it's present in the work that we're building on, although it would be a nice assumption to drop if you could. Okay, so that's all for this part, if there's no more questions. Anyone have the time? 5 till 1? All right. Then I'll go on to the last part of the talk. So clustering with grouped observations. All right, so this is yet a completely different learning problem. Just going back to clustering. So most clustering algorithms they basically assume that the clusters are non-overlapping, like methods like k-means or spectral clustering or kernel k-means and many others. They basically assume the clusters don't overlap, that there's some region of low density separating the clusters. But what we'd like to, a more challenging problem, and one we'd like to solve is something like this, where the clusters do overlap. All right, how do you recover these? How do you recover clusters in this situation without making strong parametric assumptions on the data generating distributions? Here's another way to think about the problem. Here's just a one-dimensional example. Let's suppose this is our data distribution, and we would like to extract the clusters. Well, you've probably been trained to just think to yourself, well, that bump is one cluster, that bump is another, and that bump is another, because we're used to clusters being separated by regions of low density. But what if I told you this is a mixture of 3 densities, and I am not making any parametric assumptions on those densities? Well, then there's actually a lot of possibilities. And in this case, this mixture up here is a convex combination of these 3 densities down here. And we can think of those as the clusters. So how can we possibly recover these clusters without making any assumptions about, some parametric model for them? Okay, so that's the problem of interest here. Well, to gain traction on this problem, we have to think about the sampling plan. So normally we think about IID data. All right, so here's a mixture model. And if we draw IID samples from a mixture model, it just means first we draw a mixture component according to the weight WK, and then fixing K, draw XI according to that component. And you do that independently many times, and you get a draw from the mixture distribution. All right, so this is typically what we assume. So the key concept here is that of identifiability. So when are these components identifiable? When can you take your data and say what the weights and the mixture components have to be? When are they uniquely determined? So we say the mixture model is identifiable if the data distribution uniquely determines the mixture model components. So there's a few results out there for mixture models. If components are assumed to be Gaussian, for example, then a mixture model is identifiable from IID data. That's a known result. It's also known for like binomial or multinomial mixture models. But basically, it's only known for a few basic parametric families that mixture models are identifiable from IID observations. And here I'm asking us to go to completely non-parametric models. Well, the way to do that then is to move away from IID, from an IID sampling plan. So instead of IID sampling, let's look at grouped observations. So we still want to estimate the components of a mixture model, but instead of IID data from that mixture model, suppose the data are generated in groups as follows. So first, you pick a component according to the weights WK. That's just like before. But now, having selected a component, you draw in observations IID from that component. And you can put them together in a vector. So this would be one group. And then you repeat that independently many times, and you get independent groups. Within each group, each data point is IID from some component, but you don't know which one. And so if you do that, then overall this data distribution now looks like this, where this just denotes the product measure. So this is just a simple way to express what the sampling process I described. Again, we still want to estimate these components, WK and MUK, but we get to observe these grouped observations. And the hope is that with this additional structure, now the components become identifiable under much weaker distributional assumptions. All right. So the question we looked at in previous work is, and so this is published work that came out last year. What is the smallest n? N is the size of a group, such that an arbitrary mixture of m components is identifiable. And is there such an m? Yes?
Sorry, I just want to be clear. So what you observe are the data points and their groupings, but not K.
That's right. That's right. You know that within a group, everything came from the same component. You don't know which component. Yeah, that's right. by the way, motivation for this, there's been a lot of work, or there's been some work on this problem of, it's been called like semi-supervised clustering, where, or clustering with constraints where you have like either must link or cannot link constraints in a clustering problem. So this is basically clustering with must link constraints. So everything in the same group is linked to everything else in that group. So those, you know, those belong to the same cluster. You just don't know which one it is. Yeah. So what one of my previous students showed, Robert Vandermeulen, was that every m-component mixture model is identifiable provided in the group size is at least 2m minus 1, and that this bound cannot be improved. So this is a distribution-free result. So make absolutely no assumptions on the mixing components, and but still they are identifiable from these grouped observations as long as the size of the group is at least 2m minus 1. All right, so going back to that example from before, here m is 3. So as long as we have groups of size 5, we can, these components are uniquely determined. There's only one set of components that can possibly generate this distribution. That's basically the result. Yeah.
With no I have multiple versions. With no a priori assumptions on the form of the new case. Of the
That's right.
No assumptions.
That's right.
And what do we mean by tight? If we go back onto the next slide.
So
In which sense?
yeah, so if n is 2m minus 2 or smaller, then you can find two different mixture models for which two distinct mixture models that yield the same distribution of such that this quantity is the same. In other words, the distribution on groups is the same. That's the distribution on your data. Yeah.
So is this in one dimension or like
Arbitrary dimensions.
And are the densities like known beforehand, or are the densities like being estimated also?
So this is, we're not actually doing estimation, but the densities or distributions are unknown. This is just an identifiability result, saying they're uniquely determined by the data. So in principle, we could try to estimate them. Yeah. Yeah. Then that leads to the next question: how do you actually estimate them? And that's the ongoing work. So I don't know. I could talk about that, or I don't know if it's time to stop.
We have the room till 1:30.
Okay.
So you can decide how much time for questions you want.
Okay. Okay. All right. Guess I'll keep going. I'll skip the proof ideas unless anyone's interested. Here's some related work to topic modeling. You can think of this problem as topic modeling with a single topic per document. This is what this is basically a model for, where n would be the number of words per document, and m is the number of topics. And each group is like a different document. So there's some connections to multi-view models, and then I mentioned this last problem already.
So I guess quick question. So going back to the tightness question.
Yeah.
So rather than allowing any possible mixture of size k, right? If you want to restricted attention to just a family of mixtures, so where the mixture components come from a given family, then presumably the n. So it's just a requirement on n. N need to be much bigger than the number of components, right here, but much bigger, but
Right.
yeah, at least twice the number of components, and one would wonder whether certain families, you could have n much smaller.
Yes.
Obviously, for Gaussians, n is 1. That's fine. One component.
Right.
Yeah. And so, have people studied? Okay, I guess this is fairly new, but have people studied this type of questions with?
Yes.
families?
A lot of the prior work on this setting has assumed discrete distributions,
Okay.
and like as in topic modeling. But there have been some works that have shown for discrete distributions, and which we generalize to arbitrary distributions, that show that if you assume that the components mu1 to mu_m are linearly independent, then you can get away with n equals 3, independent of m. So you need groups of size 3. So that's one example where if you do make some assumptions but still non-parametric, you can get a smaller n. Potentially, it's an interesting question is if there's a sort of a spectrum of maybe smoothness assumptions that give you n ranging from 1 up to 2m minus 1 or something like that. Yeah, that's an interesting question. And I'll mention another such result, which is right here, which actually lets us get it down to n equals 2. So it's slightly stronger than linear independence. And the reason we'd like n equals 2 is we want to design a practical algorithm. And it's just a lot easier to work with pairs than triples or higher order tuples. It's still pretty challenging, but with just n equals 2. So here's an assumption on these mixing components. M is arbitrary, n is 2, and suppose the mixing components satisfy this property. It's an implication. If a linear combination of the components is a probability distribution, then all of the weights have to be non-negative. In other words, the linear combination has to be a convex combination. Okay, so this is an assumption on the distributions, which you can argue is a little bit stronger than linear independence. And it basically says, well, what does it say? You can't take one distribution. What does it say? You can't get well, it's hard to say exactly what it means. You can't partition the components into two sets and create mixtures out of them such that they're equal. So it's a kind of distinguishability assumption. I don't know. It's implied, for example, by what's called the anchor set assumption. If each component has some subset of its support that does not intersect the support of any other component, then this is true. So under this assumption, then the mixture model is identifiable. So this is a weak non-parametric assumption that lets us get away with just looking at pairs of observations. And so if you want to design an algorithm now, you can just suppose you observe pairs of observations. The elements in each pair come from the same component. And now it's much easier to write down a model for an estimator compared to pairs of size n, right? So for example, you could, a model for a pair might look something like this, where this P is just some parametric model or non-parametric model for a density with parameters theta k. All right, so this would be the distribution on pairs. And now you want to infer those parameters. So for example, going back to this original data set, here now let's assume each cluster is itself a mixture of Gaussians. And we want to infer those components. So you can use this model and this model together to infer those components. And the assumption that you have grouped observations prevents you from just learning a simple flat mixture model of 6 components, but it rather ties these 3 together and ties these 3 together to give you an overall estimate. So that's the sort of, sorry, that's probably pretty vague, but that's the sort of thing we're thinking about right now, to try to take this identifiability theory and turn it into practice. All right, so there's a few, I sent these out if you got the email, so you've seen these, but so there's a little bit you can read about if you'd like to. And I'll stop right there. So thanks for your attention.